Carl Sagan said about Europa, "If we're looking for life in the solar system, Europa is the most promising candidate because it has everything life needs: water, energy, and chemistry." Now it's time to find the evidence. These words came in the late 1990s, after examining the first detailed images sent from the Galileo spacecraft. Those images shocked the scientific world. They showed evidence that beneath Europa's icy surface lay more water than all of Earth's oceans combined. Carl Sagan's philosophy of life formed the foundation of NASA's Follow the Water strategy. Wherever there's water, there might be life, and Europa possesses one of the largest water reservoirs in our solar system. But Europa's story isn't just about water. It's the perfect demonstration that life might be possible even under the most extreme conditions. When Galileo Galilei pointed his telescope at Jupiter in 1610, he saw 4 bright dots: Jupiter's largest moons, Io, Europa, Ganymede, Callisto, the Galilean satellites. This discovery was the first direct evidence that Earth wasn't the center of the universe. But for 370 years, these moons were thought to be just cold, dead rocks. Europa was just another icy moon in the cold outer reaches of the solar system. Everything changed in the 1970s. The Voyager 1 and 2 missions provided unprecedented close-up looks at the Jupiter system. In 1979, Voyager images revealed Europa's surface. Unlike any other world we had seen, Io was volcanically active with sulfur eruptions everywhere, yellow and red sulfur compounds painting the surface in alien colors. Ganymede and Callisto showed crater-covered ancient surfaces, geological museums of solar system bombardment history. But Europa was smooth, remarkably smooth, very few craters. A young surface, geologically speaking, active geology suggesting something was resurfacing this world. Europa's surface density is 3.01 grams/centimeters cubed, indicating a mixture of rock and ice. The interior is differentiated, a rocky core surrounded by a water-ice layer, topped by a thin atmosphere. But the most remarkable discovery was the linear features. Linea, long, straight or curved lines crisscrossing the surface. Some dark, some bright, some appeared fresh, some old. A complex network of cracks and ridges. These linea are remarkably similar to sea ice formations on Earth. In the Arctic Ocean, ice floats, cracks and refreezes in exactly the same patterns. This was the first hint of liquid beneath Europa's ice. In 1995, the Galileo spacecraft arrived at Jupiter, beginning an extended mission that revolutionized our understanding of the Jovian system. It made close encounters with Europa, capturing high-resolution images, magnetometer readings, and gravity measurements. The magnetometer data was revolutionary. Europa's magnetic field showed complex interaction with Jupiter's powerful magnetic field. Field strength variations depended on Europa's orbital position relative to Jupiter. Only one explanation fit the data. Europa's interior contained an electrically conducting layer. And in the cold vacuum of space, only liquid salt water is sufficiently conductive to explain these magnetic signatures. A subsurface ocean was confirmed, not just wet ice or slush, but a real ocean, a liquid water ocean. A global ocean encompassing the entire moon, more extensive than any ocean on Earth. Ocean depth estimates range from 60 to 150 kilometers. To put this in perspective, Earth's deepest ocean point is the Mariana Trench at 11 kilometers. Europa's ocean is 5 to 15 times deeper than Earth's deepest point. Ocean volume calculations suggest 2 to 3 times Earth's total ocean volume. Despite Europa being smaller than Earth's moon, it contains remarkably more water than our entire planet. Ice shell thickness averages 15 to 25 kilometers. Some regions are thinner, creating possible thin spots where the ocean is closer to the surface. These represent direct access points for future missions. Chemical composition is critical for habitability assessment. Sodium chloride, common table salt, detected spectroscopically. Familiar chemistry that could support familiar biochemistry. Sulfur compounds, created by Jupiter's magnetosphere bombardment. These represent potential energy sources for chemosynthetic life forms. Hydrogen peroxide, a radiation-induced compound that could serve as a potential oxidant for alien metabolism. Oxygen, produced by radiolysis splitting water molecules. O2 production in the ocean creates potential for aerobic-like metabolic processes. Carl Sagan immediately grasped the profound implications. Europa could harbor life forms unlike anything on Earth, yet they would be operating under the same physical and chemical laws that govern all life. Astrobiology rapidly developed around Europa's potential. Extremophile research intensified dramatically. Scientists began systematically studying Earth's most extreme environments as analogues for Europa's conditions. Hydrothermal vents in Earth's deep ocean provide perfect analogies for Europa's potential. The Mid-Atlantic Ridge, East Pacific Rise, and other underwater volcanic systems support complete ecosystems with no sunlight dependency. Chemosynthetic bacteria convert hydrogen sulfide and other chemicals to energy, forming the base of entire food webs.
Tube worms reaching 8 feet in length cluster around these vents. Giant clams filter nutrients from the chemical-rich water. Unique fish species adapted to high pressure and chemical toxicity thrive in these extreme environments.
These creatures survive in conditions previously thought impossible for life. High pressure exceeding 200 atmospheres. Toxic chemistry that would kill surface life instantly. Extreme temperatures ranging from near-freezing seawater to 400 Suez vent mouths. This represents a paradigm shift in biology. Life is far more resilient and adaptable than previously imagined. Ice-covered lakes in Antarctica offer another crucial analog for Europa's conditions. Lake Vostok lies beneath 4 kilometers of ice cover and has been isolated for 15 million years. Yet when scientists finally accessed it, they confirmed microbial life, ancient water-preserving biological activity through geological timescales. Lake Ellsworth and Lake Whillans represent similar subglacial environments. Each harbors unique microbial ecosystems. Life persisting in perpetual darkness, sustained by chemical energy sources. These Earth analogues conclusively prove life is possible under thick ice. Subsurface oceans are habitable environments. Europa's conditions are not insurmountable barriers to life. Salt-loving organisms called halophiles demonstrate that Europa's salty ocean wouldn't be an obstacle. The Great Salt Lake, Dead Sea, and underground salt mines all harbor thriving organisms adapted to hypersaline conditions. Some halophiles actually require salt for survival. High salinity provides osmotic balance, chemical stability, and pH buffering. Europa's salty ocean could be advantageous rather than problematic for specially adapted life forms. Deep biosphere discoveries reveal microbial communities living miles underground in rock fractures, using chemical energy from rock-water interactions. No organic matter input from the surface whatsoever. Completely independent ecosystems sustained by geochemical processes. Europa's rocky core potentially harbors a similar deep biosphere. Chemical energy from rock-water reactions could power metabolism. Radioactive decay provides additional energy sources for biological processes. Potential energy sources available on Europa include radiolysis, high-energy radiation splitting water molecules into hydrogen and oxygen. This chemical disequilibrium creates energy gradients that life could exploit. Serpentinization, water reacting with olivine-rich rock produces hydrogen gas, causes pH changes, and releases energy. This process can continue for millions of years. Tidal heating, mechanical energy from orbital flexing generates heat, accelerates chemical reactions, and provides energy transfer mechanisms throughout Europa's interior. Sulfur chemistry, bombardment particles from Jupiter's magnetosphere create various sulfur compounds, enabling redox chemistry and electron donor acceptor pairs, essential for metabolism. Chemical gradients, the ocean-rock interface has different chemistry than the ocean-ice interface. These concentration differences can drive chemical reactions that life could harness. The Europa Clipper mission, launching in October 2024 with arrival at Europa in 2030, will conduct multiple flyby missions using state-of-the-art instruments specifically designed for life detection. Ice-penetrating radar will map subsurface structure and ocean boundaries. Thermal emission imaging system will detect heat patterns indicating geological activity. Mass spectrometer will analyze atmospheric and plume composition for biosignatures. Magnetometer will confirm ocean conductivity and structure. Gravity science will reveal internal structure and ocean properties. Life detection strategies for Europa Clipper include biosignature gases, analysis of plume composition for hydrogen sulfide, methane, phosphine, and other gases that could indicate biological activity, organic compound detection, searching for complex carbon-based molecules like amino acids, lipids, and nucleic acid precursors, chemical complexity beyond what non-biological processes typically produce. Isotope fractionation. Biological processes preferentially use lighter isotopes. Specific carbon-12, carbon-13 ratios could reveal life's chemical signatures. Disequilibrium chemistry. Identifying chemical combinations that are thermodynamically unstable without active maintenance. Biological systems characteristically maintain chemical gradients that wouldn't persist naturally. Recent discoveries have been increasingly encouraging. The Hubble Space Telescope has detected water vapor plumes erupting from Europa's surface. This periodic venting suggests direct ocean surface connection and represents an opportunity for direct sampling without landing. Molecular hydrogen has been detected in these plumes. This represents a potential food source for life, as hydrogen-consuming organisms are common in Earth's extreme environments. The subsurface ocean has been confirmed through multiple independent techniques: magnetic field analysis, gravity measurements, and tidal flexing observations. The ocean's reality is now firmly established. Chemical signatures in surface ice suggest hydrothermal activity. The presence of organic molecules remains possible, awaiting more sophisticated analysis. If Europa harbors life, the implications would be enormous for our understanding of biology and our place in the cosmos. Life would be demonstrated as common in the universe. The solar system alone would have multiple habitable environments where life emerged independently in different locations. This would prove convergent evolution on a cosmic scale, similar solutions to survival problems arising independently, suggesting universal biological principles. It would demonstrate alternative biochemistry, life not requiring Earth-like surface conditions, dramatically expanding our definitions of habitable zones. It would establish subsurface biospheres as a precedent. Most of the universe's habitable environments might be subsurface, fundamentally changing our search strategies for life elsewhere. Carl Sagan would be absolutely thrilled by the Europa Clipper mission. The technology has finally caught up with his vision. We now have instruments sophisticated enough to provide definitive answers to the questions he posed decades ago. The cosmos is within us. We are made of star stuff. We are a way for the cosmos to know itself. Different chemistry, different environment, but the same universe operating under the same physical laws, same potential for complexity emerging from simple chemical interactions. If Europa has life, we're not alone even in our own solar system. If Europa doesn't have life, we still learn crucial information about life's requirements and limitations. Either outcome represents a win for scientific understanding. The search for life continues expanding beyond Europa to other promising locations. Enceladus, Saturn's icy moon, has a similar subsurface ocean with confirmed hydrothermal activity. The Cassini mission detected organic compounds in ice crystals ejected from its surface. Titan hosts methane lakes and complex organic chemistry. While it uses a different liquid medium, the complex chemistry suggests possible exotic biochemistry pathways. Mars shows evidence of ancient rivers and lakes, with current subsurface water remaining possible. Past habitability has been confirmed. Present life remains a possibility. Each location expands our definition of habitable zones. Life appears possible in far more places than we previously imagined, from the innermost reaches of the solar system to its frozen outer boundaries. Carl Sagan's optimism about life in the cosmos appears increasingly justified. Life may indeed be common throughout the universe. Intelligence might be rare, but life itself seems to represent the universe's fundamental tendency toward increasing complexity and organization. Europa represents hope embodied in ice and water. Not just the promise of scientific discovery, but the possibility of cosmic connection. Finding life anywhere in the universe proves we're not a cosmic accident, but part of a universal phenomenon. A successful Europa mission would vindicate Carl Sagan's lifelong vision. Life everywhere it can possibly exist. A cosmos filled with biology, chemistry, and ever-increasing complexity. Life finds a way, not just science fiction dialogue, but a universal principle governing cosmic evolution. Chemical evolution inevitably leads toward biological evolution. Matter spontaneously organizes into patterns that process information, reproduce, and adapt to their environments. Europa's frozen surface conceals warm oceans that may be an ancient cradle still rocking with life. Chemical evolution potentially continuing in alien seas, following pathways we can barely imagine. The life forms might be simple or surprisingly complex, familiar in their basic chemistry or utterly strange in their adaptations, but they would still be life, life in the cosmos, life beyond Earth, living proof that we're part of a universal phenomenon transcending any single world. Carl Sagan once wrote, "The search for extraterrestrial life is really a search for ourselves, for our origins, our destiny, our significance in the cosmic story." Europa continues that search in its icy oceans and chemical interactions.